with an advertisement. So I'm actually on the advisory board for this journal, which doesn't involve much work, that just started a year ago. Dynamics and Statistics of the Climate System, published by Oxford University Press. It's open access. Actually, Hank has published two of the articles in the first volume. So, and but it absolutely fits the remit of this whole summer school, really. So I just realized it's trying to fill what was perceived as a gap in the journals, and so very much on the stochastics too, and statistics. So I do encourage you, if you're thinking about publishing, and you find that maybe Physica D isn't quite right, and a journal Atmospheric Sciences isn't quite right, maybe you can consider this journal. Okay, so now we're going to talk about 2D turbulence and ozonal jets. We've talked about jets in the context of wave and flow interaction. Of course, you can also talk about jets from a pure turbulence point of view in terms of beta jets, but we talked about 2D turbulence as well, and we're going to bring those things together and then come back to the real atmosphere and talk about some of the issues there. Okay, so I already showed versions of this, I think, in the turbulence lecture. So if you look at observations of the atmosphere, they show an upscale. You can call it a cascade, if you like, of kinetic energy in the upper troposphere. The upper troposphere is the main region because of the jet streams. That's where all this action happens. But it's sort of an interesting thing. So you see something from this old Figgy data from Bourne Shepherd, that you see something like a -3, which is promising. And certainly at these, this is spherical harmonic index of these wave numbers, which are in the synoptic scale, things are pretty isotropic, that the zonal and meridional components of energy are pretty comparable. But as you come to scales larger than total wave number 8, you can see that the flow is primarily zonal, and that's just saying that we have zonal jets that really dominate things on Earth. When you look at so this is the latest when we looked at the with Sarah Burgess, looking at the Eastern WF version of this with their T800, so that's whatever factor of 25 improvement. Then this is pretty well resolved now. This aspect wasn't necessarily well resolved in the old data, but you can see that this is the flux of energy to a large scale. A negative flux, this is a kinetic energy. A negative flux means that the energy is going to a smaller wave number or a larger scale. But you can see that there is an upscale energy flux, but even if you want it to be a real optimist, it's about over a factor of 2. Well, that's not even a decade. I don't think you really want to call that a cascade. And also, if you split it up, in this case we did the zonal mean and eddy-eddy. Before I was showing stationary transient, but it's pretty much equivalent. You see that actually there's this very short peak here, which is the sorry, the blue is the total, that the red is the eddy-eddy, is a very short peak. I mean, that's 1 point. That's not a cascade. And actually a lot of it's carried by this wave mean flow interactions. That's certainly not the Craigton upscale cascade in the usual sense. So this so-called pure turbulent cascade is extremely limited. So it makes you rethink, how do we apply 2D turbulence to the atmosphere? Now Schneider and Walker argued about 10 years ago that this limited transient upscale cascade is no accident, and actually the atmosphere will adjust toward a weak nonlinearity, they called it, where essentially the most unstable scale equals the energy containing scale. So if you want to get an upscale energy cascade in the real world, you can always do it in a model, of course, but it's argued, now some of you may contradict this because this is older work and I haven't followed it, but it's argued because the deformation radius is much smaller in the ocean, that there is more room to cascade upscale, and you can see an upscale, much more of an upscale energy cascade in the ocean. Okay, but so then the question is, we have this.
So if you make the difference between cascade and upward energy transfer,
well, okay,
it may be enough to get the point. I mean, a cascade would be
right. So cascades are these step by step.
Step by step. So it's clearly not a cascade, but still you have a.
But it's upscale.
Upscale energy transfer.
Yes.
And so this is so even in very academic setup in 2D turbulence, as soon as you have a large-scale structure, a jet or vortices, this is how it occurs. I mean,
yeah, of course, there's the issue in 2D turbulence without jets where you have vortices. You could do some local analysis around that. And actually, as I mentioned in Sarah Burgess's work, she showed that the filaments between the vortices follow the Rhein scaling. So there's essentially a wave flow interaction between the vortices and the filaments. But of course, then you have to follow vortices. It's much more difficult than a zonal mean. Yep. Oh.
And how this picture change with the parameter? If you change beta, if you change the energy fluxes, the radiation, like.
Well, Schneider and Walker would argue, if it's, of course, this is a baroclinic system, I mean, the real system. If you have a barotropic system, then you have to impose the forcing, which is artificial, right? Because it's not arising from the flow itself. So to have it arising from the flow itself, you've got to have a source of energy. So in the atmosphere, that's a baroclinic instability. And they would argue that, I think they'd argue this is independent of beta, basically, that you'll always adjust to this, neutral, or it's basically, it's to this weakly nonlinear state. So there may be some things that would take you out. I'm not quite sure, because of course but I think the argument is this is general. Right, but well, you're right. So why does the ocean doesn't do this? I guess because the ocean eddies just don't affect the global scale in quite the same way as the atmosphere, because they're much more localized. Okay, but then you might say, all right, we understand that this should be upscale, and it's going to be narrow. Is it obvious that this should be upscale? So then you raise the question, why is this mixed flux upscale? And if you go to arguments, these textbook arguments for why there's an upscale energy cascade, Greg Holloway is quite a interesting article, basically pointing out that almost all of these arguments have loopholes. So it's a fun read. And anyway, they're not really relevant to this situation. Often you start with a very localized disturbance, like I showed. We have very non-local triads, and a lot of these arguments are very spectrally local. Spectrally non-local, I drew the sketch of where you have a zonal flow. Let's say if you were K and L or something, you have a zonal flow here, and then you have a triad which is like that. Go back to the OR effect, and this goes back to my thesis work. So in general, if you have a shear flow and you have disturbances, and these are just going to be streamlines for a plane wave, they'll be constant vorticity. If these streamlines are leaning into the shear, they basically get tilted by the shear. I guess it's most obvious if you think about vorticity, because that is advected. And it turns out that the disturbances grow during this part of the evolution, and they decay in that part of the evolution. And this growth part is called the OR effect. So it's amplification of waves without normal mode instability. So it's a transient amplification. So if you just put in a random set of phases, the ones that are leaning into the shear will take energy out of the mean flow so that they can grow, and the ones leaning away along the shear will feed energy back into the mean flow. So either of these things can happen. And this is just a snapshot from my old code at 32 by 32 wave numbers or something. So this is x by y, and this is the initial state, the stream function and the vorticity. So you see it's basically in a localized wave numbers, set of wave numbers. And there's a sinusoidal shear flow. And then after some time, what you see is if you look at the vorticity, what you see is that it's being shaped by the mean flow. So you can see that the vorticity is being advected, and what you're mainly seeing are these sheared out eddies. But if you look at the stream function, this is the same flow. So of course you've got to realize stream function and vorticity relationship is, well, it's del squared, but del squared is a pretty heavy filter. So this is the same flow, but this is the stream function version. That of course is a low pass filter, if you like. It picks up the longer wavelengths, and what you see are these vertically aligned, not vertical, well, vertical in the page. These are meridionally aligned things, which are basically these kind of things, right? So these are the amplifying ones which show up in the stream function. These are the ones that get these are the sheared out disturbances. Now this OR effect is kind of interesting. I guess, you know, many things get rediscovered, but maybe the OR effect is the one that's been rediscovered the most times. There's probably half a dozen papers that have discovered this solution, and people quote OR. Now it's understandable why people might not know about OR, because it was Proceedings of the Royal Irish Academy, and that's not available in many places. Interestingly enough, it's in Boston. Maybe that's not too surprising. But then I got to Cambridge, and McInerney pointed out that actually Kelvin had derived all this even earlier in the theory of sound. Actually, so you can include beta, but it doesn't change anything for this particular problem. So this is the classic shear flow problem, and of course in general there would be a curvature term here. But if you have a linear shear flow where s is constant, this is 0. So then you just have this term here, and if you put in a solution, you can get an exact solution, which actually is exact at finite amplitude if it's a single plane wave. But for the linear problem, we can imagine superposing things, and so it's it turns out you can solve it, and you write the energy as a function of k and l, the x and y wave number and time, is the entropy, which is conserved in this problem. Okay, it's exact invariant, but the energy isn't, and it takes this form. Or if you write it in terms of the initial energy, you can write it this way. The point is that if you start at, so L is the initial wave number. Maybe this is fine because this is a constant. Well, okay, this is the usual form. So this L is the initial Y wave number. K is the X wave number. The X wave number doesn't change because of the zonal symmetry. So you see that if L starts with a positive value, it could be positive or negative relative to K. If L over K is positive, then this thing's going to go through 0. So it's going to grow with time, and then eventually, as you keep time running further, of course, this is going to go to infinity, and the thing will damp. So what this gives you is, and what I did in this little note here was, well, there was an interesting debate at the time. Brian Farrell was arguing that this was a really crucial aspect of baroclinic instability, because he could find this optimal mode that would grow. And he could find a wave, a single wave that would grow. Because if you pick an initial state that's leaning far into the shear, it will grow really high. Now, Ray Pierre-Humbert's argument was, well, there's an optimal mode that will take all the air molecules in this room up to that corner and will suffocate. It exists, but it's not going to happen. So you can't just look at a single wave. That's a set of measure 0. So you should look at a distribution. So I did a little exercise here, where this is the wave number space, and it's a power spectrum. So you imagine a band of wave numbers that could be isotropic, where it's around the whole band, or you could just pick out a certain segment of wave numbers. So if you pick out a segment like Brian would tend to pick, you pick these guys here that have a very, what you want is the initial L to be large, and the initial K to be small, and then you'll get a big growth. So that's what happens here. This is the OR effect. It grows, but then for any finite wave number, it will eventually decay. But if you pick waves that are initially leaning along the I'm running backwards here. If you pick waves that are initially running along the shear, they will just decay. So that's these guys. If you pick something at 45 degrees, you get a little growth, but then it decays. Interesting enough, if you pick isotropic, it's constant, which is interesting. So turns out that in this case, there's growing and decaying waves, but they exactly cancel. And if you pick a segment that excludes these waves, just something around this point, then you get growth, which is irreversible. And that's because basically there's an infinity of waves. This is continuous, of course. And there's always going to be waves, no matter which. Any time that you pick, you can find a wave tilt that's even shallower, which is still to come. So it's like this, always more of them coming. So that's kind of interesting. But as long as you make L finite, as long as you exclude a neighborhood around 0, then the disturbances will eventually decay. So actually, in fact, Creighton had something in terms of this constant one. It's kind of interesting, and it turns out that if you have an initially random connection of disturbances evolving linearly, either the pure strain case, which Creighton talked about, or the pure shear case, which I talked about, it'll exactly conserve its energy, which means there's no zero exchange with the background flow. But in this setup, you can actually get a disturbance growth out of nonlinearity. And this was the shear flow case, Cummins and Holloway. These are the energy exchange terms, which are basically zero. And when I say linear, I mean quasi-linear in Brad's terminology, because there is the feedback on the mean flow. It's just that there's no wave-wave interactions, and so the energy is constant. But if you allow the wave-wave interactions, then the disturbances can grow. So the wave-wave interactions actually are essential. I had also gone back to my old thesis work. This is just decaying 2D turbulence. These are the energy spectra in a sinusoidal jet. And in the quasi-linear simulation shown here, this is the first time unit, and the 2, 3, and then a longer time, and also the zonal and meridional components. What you see initially is that at large scales is dominated by the meridional components. That's these eddies in the vertical. And then as time goes on, though, things get damped out. Whereas in the nonlinear state, you see, and also there's not really any anisotropy, and there should be no mechanism, because basically the eddies are evolving without seeing each other. But in the nonlinear case, first of all, things become much more isotropic, even at the large scales, and there's much less decay. So basically what happens is kind of, you can think of the wave-wave interactions, or the turbulence, you might call it, as scattering. I guess that's what the term that Brad would use, across the different wave numbers. And it means that you break up the coherence, and the eddies grow, but they don't decay back again, because they get isotropized. So basically these wave-wave interactions are rendering the upscale cascade irreversible. Therefore you get less eddy forcing of the mean flow via this straining mechanism. Back to Schneider's work. So around the same time, they were trying to understand how much you can get, how important. So they say the wave-wave interactions aren't very important in terms of the upscale energy cascade. So how important are they for climate? So they ran an idealized GCM, and they suppressed the wave-wave interactions, and they still got a -3 spectrum. Although it's not as nice as in the nonlinear cases, really smooth. It's much more jagged, but still it's sort of a -3, and you still get this downscale. And that it sort of makes sense, because even in the quasi-linear case, you still get a downscale entropy cascade, so you would expect something like a -3. But when they looked at the zonal jets that they got, it was very different. So this is the zonal mean, zonal wind in their model. This is the nonlinear simulation. This is when you suppress the wave-wave interactions. And this all makes sense, because I've just shown that if you have the quasi-linear case, if you suppress the wave-wave interactions, the eddies get over-damped, because they all get sheared out to wave number infinity, and there's too much backscatter. So the nonlinearity reduces the backscatter from the waves onto the mean flow, and the jets are much too strong in this case. So I think it really is an important.
So, in a paper we have published a few years ago, we have shown that the wave-wave interaction can be neglected in a special regime when there is a timescale separation between the time you need to build up the large scale on one hand, and the dissipation time on the other hand. And so I think that Farid Aichalal made the simulation with Tapio, the same kind of this one, rotating the Earth twice faster, and then the jet looks nearly equal. So it's a matter of regime.
I should say in my Veritrop. Thanks. And I should have, so I could point out that for those barotropic simulations, I'd chosen parameter values based on, motivated by Earth. So I was trying to be in the Earth regime. Okay, I showed this plot on Tuesday, I think. So, but then maybe it makes a little more sense now. And say in the real atmosphere, yeah.
So without eddies, jets tend to become more stronger here?
Well, in this regime, as Freddie says, you probably shouldn't take that as a general principle.
Yeah, it's kind of similar to if we see in Antarctic circumpolar current in ocean.
Okay.
So if you remove the jet eddies, so if you have a coarser resolution model, so they tend to give a stronger jet, basically.
With the wave interaction.
So basically, if you have very coarse resolution simulation, so you don't have eddies.
Well, this isn't without eddies.
Yeah.
This is without eddy interaction. So you still have the eddies in there.
Yeah.
It's just that they're being strained out. It's a quasi-linear regime. So you don't want to interpret this as without eddies. This is eddies, but eddies that aren't allowed to interact with each other.
Okay.
So it's perhaps a little different.
It's slightly different.
Yeah. Okay, so these were plots of I showed these earlier, maybe we just come back to them again. This is a constant zonal wave number plotted against a meridional wave number, or in this case, the Legendre polynomial index. And the low wave number low zone wave numbers, which are the planetary scale waves, we call them, you see that there's a spread of entropy in both directions. So you're getting these, think of the phase tilt, you're getting some like this, some like that. But they go both ways, but this is now a steady state, or statistically steady state. So it's clearly irreversible. So there's a net transfer upscale. And that tends to extract energy from the mean flow. So it acts as a damping of the mean flow. And whereas the synoptic scale eddies have this downscale cascade, and they give energy up. And people have found these results from other means. By the way, this is Dave Harbin, not Dave Lorenz, not Ed Lorenz, student of Dennis's at the time. So yeah. So you can of course infer this from other methods, but this is the way I look at it. So why is it that this upscale transfer in the atmosphere why is it that the net transfer in the atmosphere is upscale? Basically, if you plot from the eddy point, this is the zonal wave number. The mean flow is gaining, the eddies are losing, but these eddies actually gain, the low wave number, and these ones lose. So it's just because this has been bigger than that. So the transient eddies, the synoptic eddies are dominating over the planetary eddies. But that doesn't have to be true. And I did this was where I imposed a jet, and it's just a case that another setup. And in this case, it was a random forcing, but just a somewhat different regime. And in this case, these low wave number eddies actually won over that. In this case, it was a damping the mean flow. So obviously, I mean, if it's an eddy-driven jet, by definition, the transfer has to be into the eddies. And then actually, the question isn't why the energy the question isn't why the energy transfer is into the jet. That's a tautological question. The question is how that arises in the first place. But of course, the jet can be there for other reasons, like the Hadley circulation or something, or the Arctic, or there's all sorts of thermal reasons why you might have jets. And in this particular case, it certainly can go the other way. Now, so I'll give an example of an eddy damp jet, actually, the stratosphere. So I've talked about that. I can't give much about the stratosphere. And I like this plot. I guess maybe it's confusing, but it's really nice. It's from observations, and it's plotted. This is from the old NCEP reanalysis, but in the northern hemisphere, there's a Berlin data set that goes back to the 50s, and actually it's considered quite reliable because of all the radiosondes. This is the polar temperature at 30 hectopascal, which is approximately 25 kilometers. It's a seasonal cycle, and it's just a histogram of each of the years. And so this runs from, in the southern hemisphere, from December through June, July, so the winter's in the middle, and then November. And for the northern hemisphere, runs from June, July through December, so the winter is in the middle. And you can see that the southern hemisphere is much colder, and by thermal wind, that implies a much stronger vortex. In the northern hemisphere, it's weaker and warmer, and that's because we have more planetary waves. There's a Charney-Drazin theorem that tells you that only the planetary waves can propagate into the stratosphere, and there's more topographic, continental contrast in the northern hemisphere, so we get much stronger planetary waves. So in this case, the wave forcing is acting as a damping. That's because it's not generated by the vortex. The vortex is actually stable. It's being generated from elsewhere. In this case, from the troposphere. Yep. Oh, Charny-Dresden theorem is just an equation for the propagation of Rossby waves, and so it's just to say that the waves become evanescent as they propagate up into a shear flow, an increasing flow, if the wave number is too high. So it depends on your regime. You just look at the dispersion relation. Obviously, stationary. Well, you usually apply it for stationary waves, but it's the basic explanation that only the longest waves can propagate up. But it just follows from the dispersion relation. Maybe this is a bit complicated, but it's nice to show measurements, and it relates to something. So ozone is, of course, a very, very important feature. These, if you look at the ozone in the fall, winter, spring, summer, basically ozone, generally speaking, it builds up. So although it's kind of ironic, but if you look, because of course ozone is created by sunlight, but if you look at the distribution of the total ozone seen to the surface, and say at the higher latitudes, it builds up, and then decays, and it builds up because of transport. So there's a seasonal cycle. So you can look at the ratio of the springtime maximum. I haven't drawn this quite right. Springtime maximum to the summertime, and that's what's plotted here. Is the ratio over the polar latitudes in the northern hemisphere between March and September, and in the southern hemisphere between September and March, so just 6 months out of phase. And so if you have more wave forcing, then you have more ozone transport, and you have there's also, of course, ozone loss because of chemistry. So in practice, this thing will drop, and it may drop a lot in the southern hemisphere. We don't see the ozone hole exactly, because this is all the way to 50 degrees. You can see the ozone hole in these plots. But the idea is that if you have more wave forcing, then first of all, you have more ozone transport. So this basic curve is going to get pushed up. But you also have a weaker and a warmer vortex. And a warmer vortex means less ozone loss, because the ozone loss happens through polar stratospheric clouds that only get formed when the temperatures get cold. So this also goes up. So for both reasons, more wave forcing involves less ozone loss and more ozone transport, and therefore a bigger ratio between this peak and this. And if you plot the amazing thing about, so this is what's called the winter heat flux, but that's actually the vertical Elias-Palm flux. So it's a pseudo momentum flux. And you see that actually, if you put the southern hemisphere and the northern hemisphere, the reason to look at the ratio was to be able to put the southern and the northern hemisphere on the same plot. And actually, it's kind of incredible. They follow this straight line. These are just images from satellites of an ozone hole in October, and a case over the northern hemisphere when it's quite a lot of wave forcing, a case in the northern hemisphere where there's not much. This is about one of the coldest. This would be what you might almost call an Arctic ozone hole, although not quite. And this is the weakest ozone hole seen in the southern hemisphere, which was in the modern era because of a sudden warming. Anyway, you can see this sort of. It's an eddy. It's a wave damped vortex that has tremendous implications for ozone. I'm going to just say one very quick thing about beta plane, about the spontaneous generation of jets. There's, of course, a huge field on this. I'm thinking of the Earth, where we already have jets for all sorts of other reasons. So that's why I didn't really want to focus on this. But as you probably all know, if you start without jets, then you'll form jets. And I think Bill Young will almost certainly talk about this. And so what you find, this is an initial state here. This is the PV anomaly. So it's Q minus. Sorry, this is initial Q minus beta Y. So what you get these zonal jets. And you get something called the Rhein Scale, which you can argue about, but let's just take it as the definition. So you wind up with these jets that pretty much have a meridional spacing given by this Rhein scale. But depending on your regime, this is a case. So there, you have a scale where you're forcing, and a Rhein scale. And if those scales are too close together, then you wind up with this sort of a situation where there are jets, but there's a lot of variation. But if you have enough dynamic range and enough spectral range between the input range and the Rhein scale, then you get this very, very smooth. These are instantaneous snapshots. This is Richard Scott and David Dritchell, and you get these PV staircases. So just to say that you can of course get jets out of turbulence alone. Just want to make sure. Okay, so now I'm going to so that was sort of the idealized stuff mainly, but now I'm going to come back to the atmosphere and talk about a number of the complications that kind of. First of all, are there any questions on anything up to this point? Because I'm going to change gears a little bit. Yeah. Oh, we've already, that came up earlier, but yeah, so it's already been talked about. Flattened jumps. Okay. So I'm going to talk about things that are sort of complexities, let's call it. So if you think of interaction between turbulence and jets, what are the things that complicate this? Of course, the first thing is the Hadley circulation. It's a big thing. So I showed you the plot from Tapio's review paper that you can argue that the extent of the Hadley cell is controlled. Always should be careful with that word, but controlled by the eddies, because the extent of the Hadley cell coincides with the point where the eddy momentum flux convergence switches to divergence. But of course, what determines the eddy flux, the eddy momentum flux? And actually, in a sense, that's just a diagnostic relationship. And you should always be careful about a diagnostic relationship because you don't really know the cause. So it's interesting that when you look at how the atmosphere responds to El Nino, this is Liu, Chen, and Frierson. Of course, there's been a huge amount of work on the teleconnections from Hoskins and Caroli. These are Rossby wave trains. It turns out to be a zonally symmetric response that I guess wasn't known. People didn't really look for it. This is Liu, Chen, and Frierson. So this is the temperature. This is in observations, I'm sure. I haven't said it, but it must be. El Nino minus La Nina. So of course you get warming of the tropics, as you expect, but you get cooling of the mid-latitudes. And if you look at the winds, it turns out that there's an equator shift of the winds. So if you diagnose this, you find that it's driven by a meridional shift in eddy momentum flux. So I showed you the Randall and Hell plots earlier. That this is similar, except they don't plot EP flux divergence. They plot momentum flux convergence. So that's the horizontal component of the EP flux. But that's why we don't see. That's why we have all this stuff in the middle. If you just plot the EP flux, you just find stuff around the critical layers. But if it's momentum flux, you just get this horizontal component. So this is from the observations. This is from the GFDL model. And just to it's a bit of a complicated figure, but the climatology is the shading, and so we have the momentum flux convergence here and divergence here, convergence here, divergence there, and the contours are the changes. So we see that the blue moves this way, the red moves that way, and so on. Although there's a little bit of red here. Oh, sorry. This is the La Nina case where the jets shift poleward. So the simple argument is that the temperature change that of course you start with a warming of the tropics, and that alone is going to change the winds, of course, in the upper troposphere by thermal wind. That will have an effect through critical air control. It'll shift the eddies, and that'll shift the circulation. So that's the argument. So that makes sense. Those are kind of arguments that I think are causal, because you have this because no one believes that ENSO is really driven. I think that's true. Driven from the exotropics. I mean, there could be noise, but fundamentally, it's not. I'm going to talk about model biases. So it's for dynamicists, there's this problem that the jets are in the wrong place, and not by a small amount. So up to 5 degrees, which, okay, if you're a GFD person, what's 5 degrees among friends, but if you're trying to do climate change impacts, that's a big thing. So this is, I've talked about the annular modes. There's various ways that you can look at the jet latitude, but in this paper by Ed Gerber and collaborators, it was the node of the annular mode variability. So the annular mode is this wobbling back and forth. So you have the jet, let's say, like this. This is latitude, and then the annular mode might be something like this. So the node is sort of at the center of the jet. And the black is the observations, and the colors are all these different models. These aren't CMIP, but it's this CCM Val, but it was similar. These are models with chemistry, but that doesn't matter. So you see that in the, this is all the way up to the stratopause, because they were stratospheric models as well. But if we just focus on the troposphere, you see that almost no models are at the right place, maybe one, but they're almost always equatorward, and that's true in the northern hemisphere too. It's seen in a couple. It's seen in a couple models, but actually it's seen if you put in the observed SSTs. So it's pretty clear that the errors arise, at least in approximate sense, from atmospheric processes. This isn't because of ocean problems. So there's something very, very wrong with what the models are doing. So of course people have been struggling with this. It's one of the major challenges for dynamicists who are working on the models. So it was also Gang Chen and Heldon Robinson. They had done this nice experiment in what's called the Held-Suarez setup, which is a very idealized GCM, where the radiation, it's a dry model. The radiation is Newtonian cooling. That's probably not, maybe well, that's actually part of the reason, and the drag is Rayleigh friction. So these are pretty unphysical things, and well, Newtonian cooling isn't unphysical per se, but of course you don't have a Hadley circulation that's anything like the real Hadley circulation in a dry model with Newtonian cooling. But that they found there was that if you change the drag, the surface drag, so they just change this Rayleigh friction in the lowest part of the atmosphere, and they got a poleward shift of the jet, and not a small poleward shift, tens of degrees. So, of course, as you weaken these were time scales, damping time scales of 0.5, 1, and 1.5. So as you make the damping time scale longer, as you expect, the jet gets stronger. Well, that's not too surprising, of course. And in the lower latitudes, that's just what happens, and they have two different resolutions here, but they give the same answer. In the lower latitudes, as you decrease damping, the winds just get stronger. Well, that's obvious and not too surprising. But in the northern, in the higher latitudes, you see this poleward shift. So they analyzed this, and they found that the mechanism was that as you got stronger winds, then the baroclinic eddies got faster phase speeds, and then when you apply the critical error arguments, the faster phase speeds implied that the braking should occur more poleward, and then that would give you this poleward shift of the jet. So it's a nice theory. It works for this model, but in the hierarchical thing, that this is where the hierarchy ends. So as Hank was saying, sometimes it works, sometimes it doesn't. So Ina Polichuk, who's in my group, when she just redid this experiment basically with full physics. So this is a GCM. It's the NCAR CAM. So by full physics, we mean there's a proper boundary layer that conserves momentum. There's moisture, there's clouds, and so on. But in an idealized configuration. So it's quite common now, people are running these models in what's called Aqua Planet. You must have heard about Aqua Planets last week, probably from Caroline. The idea is you just have water everywhere, no land. So it's, it takes out some of the differences. So it's sort of the simplest setup that you could use for a GCM, but with full physics. And you can't, of course, change a Rayleigh friction, but what you change is just the momentum or roughness lengths, especially at the small wind speeds, which turns out to be where the observational constraints are very weak. Turns out we also got a poleward shift, but for completely different reasons. So, and I guess a tropical person would say, come on, you guys, how could you, forget about the tropics? So in this case, it happens, and you can show that if you just change the roughness over mid-latitudes or tropics, it's all coming from the tropics. And it comes actually because the roughness affects the moisture flux as well, and the heat flux, but mainly moisture flux. And the moisture flux changes, you have, and that changes the Hadley cell, and then that changes the jets. So this is just the jet shift, and we do the same critical layer kind of argument, and you can show that the critical layer shift accounts for the change for the poleward shift of the mid-latitude jet, but ultimately the driver is coming from the change in the tropics. Just to say that we also did it in what's called emit mode. So emit mode is where you put the continents back in and you use observed sea surface temperatures, and it's the same thing. So this Aqua Planet setup seems to capture the response in the full system. Yeah. In fact, I said, I didn't say La Nina, but it's exactly like a La Nina, and it's really the same. So we basically figure it's the same mechanism that Chen Lu and Frierson found for ENSO, but to reduce the roughness is like La Nina. Well spotted, Joy. Well, in the exchange, so when I'm not a boundary layer person, but in these boundary layer formulations, it all depends on, you have a roughness length, which is to do with the roughness of the lower surface, and that ties in to the mixing length, and then but you can start from just a momentum transfer in the surface stress equation, but of course the same motions are affecting heat and moisture, so the roughness length comes into the moisture as well. But it's basically just to do with the surface stress, that if you have a more ragged surface, it'll be more damping. But it's like a parameter that you're almost going to have in a boundary layer scheme. It's like the surface drag. So basically, if you reduce the roughness length, you're just changing the surface friction. But of course, that doesn't mean that the surface stress changes, right? It just means that the surface friction, which the zeroth or the first order response as the winds then would speed up, and you might wind up with the same stress, and you might wind up with the same solution. Actually, that would be what I called before the large-scale dynamicist view, that if you just change the boundary layer, nothing changes because it's all controlled by the eddies. And all that happens when you change the boundary layer is the surface winds get weaker or stronger, but you have the same stress. But it's obviously not true because there's this big feedback on the eddies. But in this case, it's coming through the moist processes. So this is sort of a weak, it's the kind of thing that makes you worry about using this. I think there's really a move away from dry models in the atmospheric community. If you want to connect in the hierarchy, I mean, there may be certain aspects that work, but you have to be very careful. Okay, the question came up about stationary waves, and I said I would answer it on Friday. Actually, I'm not really going to quite answer it maybe the way I should have. So let me just, I think the question, I've forgotten who asked it, but it was the question, how do the stationary and the transient waves interact? So one of the aspects is that the stationary waves, of course, create a zonally varying background state. And so if you want to look at things like this Elias and Palm wave activity, you have not a zonal mean background state, but you have a zonally varying background state. So that means you can't use pseudo momentum because you don't have a translational symmetry. If they're stationary, you could still use pseudo energy. So you can get a conservation law, but then you don't have a relationship back to the mean flow. So you can't relate that in any obvious way to the mean flow change. You can try to get a mean flow theory, but then you have to make other approximations. And so there are some papers by Hoskins. Oh, help me. What's the? I don't think it's the 80. It must be 83 or something. I mean, gosh, there's so many. But it's about it's the E vector, I think, paper. Hoskins, James, and White. Does anyone know this one? Anyway, it's around there. And then also Plum had some papers around the mid 80s. So they had tried to tackle this, and they got some partial equations for the interaction between transient and stationary eddies, but it's not neither is a complete theory. So we don't really have a complete theory in the way that we do for the zonally symmetric case. So that's the mathematical answer. And then the physical answer is that, of course, we have these longitudinal, the stationary waves, of course, create is equivalent to a longitudinally varying jet. And this is a nice figure. It's in the Hoskins. This is a nice review paper, basically, of possible dynamical mechanisms before changes behind changes in weather extremes. But actually, they sort of said, well, we don't understand how weather extremes might change. So let's just basically review atmospheric dynamics. So it's a very nice review of some, although short, of what's known about dynamical mechanisms that might be relevant in climate change. But it's certainly it's just a list of things that could be playing a role. But this is, but it goes back to Hoskins and Ambrizzi. So this is like a refractive index here, and what they plotted are waveguides in the double arrows, and also some preferred pathways that I guess are Rossby wave trains, and for stationary wave propagation. And you can see that it's complicated, and you can obviously see also why when we look at the eddies and the storm tracks and the jets, we don't see a zonally symmetric signal. So part of it's baroclinicity, of course, but part of it's also the fact that this is upper tropospheric, that you have this waveguide structure. So the waves are not just propagating equatorwards and poleward like I drew in this simple picture. They're also propagating longitudinally. So of course we know that this is going to be a very complex situation, and you're going to have a strong role of the stationary eddies in where the jets are. Someone had asked about resonance, and the Potsdam group, and I think they kind of are using this waveguide as a resonant channel. But as you see, it's not a strict resonant channel because it doesn't go all the way around. But it is possible. So you could say it's nonsense, which certainly some people do. But you could argue there's something to it. And actually, since I think we have time, I've mentioned McIntyre many times, and one of the things, I guess for me, it was a pretty important thing, because when I got to Cambridge and they were working on this critical layer stuff, I should have put the plot in. McIntyre and Palmer had published the first maps of PV in the stratosphere, and they found this big cat's eye structure, wave breaking, like this in the PV, and he was working on this critical layer stuff with Kelworth and Peter Haynes were working on critical layers. And I said to Michael at some point, "You're not seriously telling me that this is a critical layer? Like, how can a mathematical object in some limit of epsilon going to zero?" He said, "Of course it is." And I thought, come on, you're got to be exaggerating. But I had a very narrow view. To be mathematical, it has to be rigorous, and you have to be in this limit of epsilon going to zero. But the point is, it's a clean limit, so you know what's going on. This is a really nice thing about asymptotics, is you don't have to be applying it in that limit of epsilon zero. Then it's absolutely clear and unambiguous, but you can pick out the essential ingredients, and if those generalize and you can come up with the right measurement, then that's the right thing. So I think so that was very important. Now, why did I bring that up? Yeah, okay, so maybe it's the case that this is not a pure resonance, but maybe there's a way that you can still get waves to really amplify rapidly, stationary waves, of course, and create wavy jet streams in this region, which is a very hot topic at the moment. Oh, yeah, sorry. Yeah, Joy.
So given that the fact that it's so inhomogeneous and you have stationary waves,
your mic may not be on, is it? You got to speak a bit louder.
Yeah. But still, the zonal mean idea of the eddies forcing the jet still holds.
It holds because you're allowed to integrate. I mean, of course, integration and averaging are the same thing, but somehow people don't like zonal averaging. But you can integrate. That's allowed. I mean, it's a periodic system. So there's nothing wrong mathematically with those equations for the eddy forcing the zonal mean jet. It's just that if you interpret them, you've got to be careful. If you're going to use a linear theory about a zonal mean flow, you have to ask, well, is this zonal mean flow actually a good basic state? Because the eddies in this part are seeing this flow, and the eddies in that part are seeing that flow. And also the eddy term, of course, is more complicated to interpret. So there's nothing wrong with it. It's just that it's just a budget constraint, and like any budget constraint, you have to look at the causal elements of it.
Looking at this figure, it looks like the northern hemisphere actually has like double jets. But
Oh, these are wave. Well, yeah, it does actually.
and the southern hemisphere doesn't necessarily.
Yeah. Well, there's the one over Australia here, maybe. It is true that the jet does become sort of double, just barely, in the sense that that you build up this jet. I think we could. I don't have the plot, but if you look at the plots I showed on the first day, you can see that there is a jet that forms. Here they have it coming much further back. I think if you look at the wind itself, it's just sort of tends to be forming here, and actually builds up here. So it's not. It's more like almost a spiral, except it breaks in pieces. But you have this part, and then you have this part here. So they are different jets, and yeah.
So the colors are the zonal velocity?
No, it's like a refractive index or something. It's a measure for the waveguide. So just to say that there's this sort of, this everything, you can apply a Ross wave theory, but then you've got the stationary waves, and then once you think of the transients, they're acting on top of this very complicated structure.
Oh, sorry. Ted.
Yeah. Sorry. Let me, before I say that, just hold that thought. These are the waveguides. So it doesn't mean there's a jet there. But of course, you can form the jet, which is maybe telling you something, because actually this does correspond to the jet here, but there's something, so it doesn't have to be exactly the same. Yeah. Well, there is something plotted here, contours. Yeah, sorry.
I wondered if you could just repeat what you meant by the preferred pathways and stationary wave propagation.
Well, gosh, I should have. This always, it's a lesson. Don't put up a figure unless you know everything that's in it. So preferred pathways are going to be. So you know about ray tracing. If you have a local source, you can follow the ray tracing. These must be Rossby wave pathways for stationary waves for certain classical sources. Like this is obviously ENSO here, right? And they've picked up some. So this is Atlantic Ocean SSTs or something. So I think they must have, because obviously there's ray paths everywhere, but they must have picked these for particular reasons, either because of the sources or else because of the mean flow conditions. Then this refractive index. So this is what's called a waveguide, where if you have waves that are on the wave, they have to follow along it. So like the edge of a jet is typically a waveguide. Does that help? Yeah. But anyway, go and. But I guess you should look in this paper probably, because they don't say this is an overview. Yeah.
It looks like the jet is kind of have a wavy structure in it. So I was curious, does the barotropic instability plays any role here?
Barotropic instability. There was some interest in the African easterly jet being barotropically unstable. I guess that's still talked about, but in general, none of these jets are barotropically unstable. The PV gradient is always positive. So the only instabilities are going to be, well, from a zonal mean point of view, from a Charney-Stern point of view, they're all going to be baroclinic. Now, conceivably, you could have barotropic instabilities because of the longitudinal variation, and there was a paper a long time ago by Simmons, Wallace, Brandstetter, 83 or something. I don't think anyone's followed. I mean, growth timescales are 50 days or something, so no one really talks about barotropic instability, except, as I say, there's this African easterly jet phenomenon. Yeah. Okay. Right. Now, so I'm going to advertise some of the work from my group. So this is most of this stuff I've done 25 years ago or something. So we've talked about how the jet responds to surface friction, even in a zonally homogeneous case. But also, I've just shown that the stationary waves play a large role, and the stationary waves are forced partly by land-sea contrast and partly by topography. And the way that the drag over topography is represented is not very systematic in models. And so student Annelies van Niekerk, who's just graduated, now she's at the Met Office. This was actually work done with John Sonoka in Canada. But her thesis was on sensitivity to orographic drag, which as I mentioned at some stage, the different modeling centers handle this very differently, as it turns out. So there's something called the low-level blocking, which is the Lawton-Miller scheme. Francois Lott is the classic scheme that's typically used for this. This is if you can't generate gravity waves, then the flow has to go around the mountain. And so that parameter is uncertain. And so what she did here was just, I think this is actually without any low-level blocking and then adding it back in. And when you put it back in, you find that the stationary that the jets shift poleward. Now, don't look at the stratosphere because that's not really important for this argument. The important thing is what happens in the troposphere. So the contours are the background state, and the shading is the shift, and you see that there's a poleward shift in both hemispheres. So that's important because it means that this parameter, which is not pretty well known, has a pretty big impact on the jet. Oh, and I should say, at Eastern WF, I showed you that plot of the forecast skill, and basically the I can't bring that up quickly. The forecast skill over time in the Eastern WF model. So we have these, 1-day forecast, and what the weather people tell you is that basically the skill has improved by 1 day every 10 years. So every 10 years they have the skill of the 3-day forecast today is the skill of the 2-day forecast 10 years ago, and the skill of the 1-day forecast 20 years ago, if you follow me. So you can imagine how much effort goes into improving. They're trying to march up this curve, and huge. I mean, it's a huge activity. Irina Sandu took out the blocking scheme, and actually most climate models don't have this low-level blocking scheme. If she took out the blocking scheme in the forecast, in the Eastern forecast model, they lost 1 day of forecast time. So they lost 10 years of model development just by the low-level drag term. So it's really important.
So can you explain what is the low-level blocking?
Just that
and the low-level blocking scheme?
Oh, well, I can't talk about the scheme, and I may even get some of this wrong because it's bad having Oliver in the back. Otherwise, I could maybe fool you. So if you have a mountain and you've got a stratified flow, then the air hits the mountain. So then what happens? It could go up and over the mountain, but of course that costs energy because it has to move at higher altitude. So there's a measure of whether there's enough energy in the upstream flow for this to happen. It's the Froude number. So it's over n. H, so n is the Brunt-Väisälä frequency, h is the height of the mountain, and u is the wind. This is the Froude number. Actually, the mountain people take the inverse Froude number, but it's the Froude number. And so, of course, if the you can call it that if you want. You can always define it to be the inverse. That's fine. Okay, so if the speed is fast enough, or the stratification is weak enough, or the height is low enough, then of course the air can go up over the mountain, and that'll generate gravity waves. We see Lee waves. Those waves propagate up. Actually, they carry momentum, and they exert drag, which is quite important. So every model has a orographic gravity wave drag parameterization scheme. I think you just can't get away without that. But it could be that the Froude number is too low, and then you can't ascend the mountain. So then you have to go around the mountain. Well, that depends on your mountain. If it's the Andes, you might have a long way to go. So, but the flow has to go around the mountain, so it's basically blocked by the mountain, and you're going to set up pressure differences, and that's going to create a pressure torque because you have, say, high pressure here and low pressure there. So that's going to, there will be a torque exchange, and also it'll deform the flow. So that's this low-level blocking scheme. So it has to decide on what this Froude number is, but that's just complicated because which wind do you pick? This is very, if you have an idealized flow, you can do all this, but in a GCM what do you really take as the wind? And so there's a lot of choices here and a lot of freedom. Yeah.
So those mountains, they are subgrid scale mountains? In
No,
the
no,
model?
no. Well, these. No. Actually, this is dealing with. Well, it's. I think the Lawton Miller is dealing. I could be wrong. I think it's. Well, okay. Of course, the blocking effect would have to be. Yeah, it must be dealing with some. But there's also a subgrid scale roughness. So I'm not quite exactly sure at what point. In fact, what point they go between one and the other. But it's basically, yeah, it's dealing. It is dealing with this. Yeah, no, that's right. It's dealing with the subgrid orography. And actually, one of the interesting things, the modelers tend to filter the orography before they run the model, because otherwise the model blows up. So this is the weather forecast models. So actually, the subgrid scale orography, they're missing a big chunk of the orography, which isn't resolved and isn't in the parameterizations. That's one of the issues too. So there's a lot of technical issues, but it's a parameterization of the subgrid scale effects. Yeah. Other questions? Anyway, so it's clearly an important term. It gives you a big leverage. But when you go to say, why does this happen? So in the northern hemisphere, it's all happening because of the stationary waves. I mean, you change the low-level drag, you change the stationary waves, and that changes the momentum fluxes. And that's what the paper's about. It turns out that in the southern hemisphere, there's also shift, but of course the stationary waves are much weaker. And if you look at the budget, it's the transient eddies which do this shift. So that's a bit more complicated, because now we have a feedback between the drag and the transient eddies. Felix Pathon, who had been in my group, had done this with a Met Office model and got a similar result in the southern hemisphere. I think it's robust, but this is a case where it'd be much more complicated to understand what's happening, because you're going to have to, obviously the transient eddies are not directly affected. I shouldn't say obviously, but presumably they're not directly affected by this low-level drag. So it's a way more complicated case. But in the northern hemisphere, it's from the station wave. So this is going to be an uncertainty in your jets, and actually it affects the climate change response, which I won't talk about. This is work with Giuseppe Zappa, who's a postdoc. Actually, it's called Storylines of Euro-Atlantic Circulation Change. So we got away with that title. It's been known that part of the uncertainty in the circulation response to climate change depends on things like how much the upper troposphere warms and so on. So so it's been called a tug of war. So what we've done here is so people have shown this in lots of idealized experiments and so on, and Manzini et al. Had a paper using CMIT models. What we've done here is, first of all, normalize by the global mean temperature, because of course models warm at different rates, and for any given model, the response is proportional to the warming. So if you really want to look at things properly, I think you have to normalize by the global mean warming for each model. And once you do that, there are three drivers, you could say, which really explain a lot of the spread in the mid-latitude circulation, especially over Europe. So one is polar amplifications. This is just looking at the CMIT models, and it's just statistical, though we've done lots of, leave one out tests and all kinds of stuff like that. We're pretty confident. So the contours are the gray contours are the climatology. So you see the Atlantic jet. This is now the lower tropospheric wind, which Giuseppe prefers because of the impacts aspects. So we have a Pacific jet and Atlantic jet, and you can see that if you have more polar amplification, that will weaken the jet, as you would expect, just from thermal wind, right? Because if you have warming of the Arctic by a thermal wind, that should weaken the jet around here. And actually, in the Pacific, actually, well, it's a strengthening of the jet. In the Mediterranean, it's a strengthening of the winds. Just actually a reduction of the easterlies more, I think, here. The tropics goes the other way. So this is the ratio of the upper tropospheric warming to the surface warming. So it's the vertical amplification of the tropical warming, which is also uncertain, and there's a big spread in models. And you see, in this case, it goes the other way. Now we have a strengthening of the jet in the Atlantic, a poleward shift. People talk about poleward shifts, but this is not a poleward shift. This is a strengthening. So you should probably disabuse yourself of that concept in general. Already I mentioned for the NAO, I mean, it doesn't project on the it projects too much on the NAO, and that's not really what this climate change signal doesn't project on the shift. So what we see here is now it's a strengthening of the winds over northern Eurasia rather than a weakening. So that's a tug of war. These things are all operating in different directions. Turns out something that not a lot of tropospheric people necessarily know, but they're learning, is that the response of the stratosphere to climate change is a huge factor. So the stratospheric vortex could either weaken or it could strengthen, and no one, has a theory, as far as I'm aware, for any of it, or even for how it might happen, really. So that's another player. That's a little bit of a different pattern here. That's also a strengthening of the winds, but this is more like an NAO type pattern here, and you see now a big effect in the Mediterranean. So so if we think about climate change, you can't just, people have made arguments, the baroclinicity will change the eddy phase speed. Well, that's so idealized. I mean, how could that one factor possibly explain? You've got all these different things, and this is uncertain because of uncertainty in polar amplification, which has a lot to do with stable boundary layers, which is a problem that all models have. I mean, stable boundary layers is like the hardest boundary layer problem there is. This has to do with upper tropospheric, so it's going to be, of course, upper level clouds and static stability and convection. And this probably has a lot to do with gravity wave drag, although it could also involve other factors coming from the troposphere.
Can you say again about what's the relation between the polar amplification and the boundary layer?
Oh, okay. So so in the tropics, if you warm up the surface, it basically it just adjusts because of convection, and you go to this moist adiabatic lapse rate. So the warming from the surface, because the warming from the surface then fills the whole atmosphere. But in the Arctic, especially in the winter, so the amplification is in the winter. Actually, this was a comment that Tapio made. I have to say I didn't agree with, because the ice albedo feedback, of course, the sunlight's in the summer, and that's when you get more absorption of sunlight if you have less ice, but it goes into the ocean. And then in the winter, when the ocean's warm and the atmosphere is cold, it comes back in the atmosphere. So the fact that the atmosphere warms in the winter and the sunlight is in summer is not evidence against the ice albedo feedback. It's just lagged. But actually, Felix Bethon, who I've mentioned, has looked at this in the different models, and the ice albedo feedback is an important part of Arctic amplification. But that's okay. There are sea ice issues, and Ken Golden talked about that. So there's a certain amount of uncertainty in sea ice. Actually, another feedback is the Planck feedback. The fact that if you have a lower temperature, so sigma t to the fourth, these outgoing radiations, so you have to warm more if you're at a lower temperature. And that's actually, so that's basic physics, and that's actually about a third or something of the Arctic amplifications. That's kind of good to know. But then another part is this boundary layer, and that's that in the wintertime you've got very, very cold temperatures, of course. So there's not really a convection at all, and you have a very stable boundary layer. So when the heat comes out of the ocean, it gets trapped in a very low layer, and so it doesn't hit the upper troposphere where it can cool to space. And so there's something called the lapse rate feedback. I don't know if anyone had talked about that, but it turns out the lapse rate feedback is a different sign in the tropics than the exotropics. So the uncertainty in that is very important in terms of, because you have to get the heat out of the system. And the depth of the layer, I mean, roughly speaking, if it's a very shallow boundary layer, then the heat's going to be very warm. But if it's a deeper layer, then it's not as warm, and so on. But anyway, but the boundary layer is not, there's a huge, I mean, no one really knows how to parameterize this. There's all kinds of field experiments up in the Arctic, and I don't know anything about all that. It's just a very uncertain part of models, and it's a very uncertain part of weather models too. But it's good because the heat gets trapped rather than spreading through the atmosphere and cooling off to space. So all this to say is, if you're interested in climate change, and you want to understand the circulation, you can't avoid some of these kinds of issues, because they're going to be a major player. You're not going to be able to just apply to something like a phase speed argument, I think. Okay, another thing, this is maybe the sorry if I'm boring you with pictures from my group. This is a student, Nick Byrne, who's about to graduate, and If you look at the IPCC and you look for, of course, they're all about detecting and attributing climate change. That's the sort of first order of business of IPCC. So if you look at the dynamical aspects, I talked about the NEO, but that's no one believes that anymore. The only attributed circulation change that's attributed to anthropogenic forcing is a poleward shift of the summertime southern annular mode, which we can call the eddy-driven jet. But it's not greenhouse gases, it's ozone. It's still anthropogenic because it's CFCs, but it's not greenhouse gases. So we still don't have an attributed circulation change. I mean, that's been accepted. There could be papers, of course, but that is accepted by IPCC on the greenhouse gas. But anyway, it's certainly attributed to the ozone hole. What happens with the ozone hole is that the vortex, of course, you have less ozone, so the vortex absorbs less sunlight, so it gets colder and stronger, and the breakup, there's a seasonal breakup of the vortex as you go into summer, because the thermal inertia of the stratosphere is very small, so you go into easterly flow when you warm the pole. That gets delayed, and it's been delayed by about 3 weeks. I should say this is still, but this affects the surface jet. The mechanism is still not understood, which is, it's kind of interesting. The strat-chop coupling problem, which I won't really talk about, but it's really still no one has a mechanistic explanation of this. So that's really still a puzzle, but it's very robust. You see this in any model, basically. So it's been interpreted as a poleward shift, and what Nick has argued in this paper is that actually that's the wrong interpretation. That actually, when you interpret it as a poleward shift, that's where you look at anomalies as departures from climatology. So you say, I've got the average temperature or the average winds. This is the the tropospheric average zonal wind up to 200 hectopascal or something, and these contours show the climatology. This is the mean, and these are I think 1 and 2 sigma or something. And you see that there's as you go into the southern hemisphere summer, there's a poleward movement of the jet. So it's actually got a semi-annual oscillation, and it's got a minimum. It comes to lower latitudes in the summer. And he's argued that you shouldn't look at anomalies as the variability as anomalies around the seasonal average. You should look at anomalies that the seasonal cycle varies. So rather than thinking about let's say you have this seasonal cycle here, where you have sort of noise around here, you should think of it that actually it can do this, or it can do this, or it can do this. So of course, mathematically, a delay in the shift and an anomaly around the seasonal mean is equivalent. But as soon as you think about a noise model, this will be very different. So it's got, I think, pretty deep implications. It's like a regime. So there's a regime transition, and actually he's shown that and argued pretty convincingly that there's a regime transition in the summer in the troposphere. The transition from the spring to the summer state is a regime transition, and it's very smooth here. But if you look at individual years, it's very sharp, and it's tied to the breakdown of the polar vortex of the stratospheric vortex, which varies. Anyway, so I think that's kind of an interesting thing too, because a lot of the people have come up with theories about eddy feedbacks. How would you get a poleward shift? That maybe the eddies respond in a certain way, but then you're very much thinking about anomalies around a mean. And he's just saying that's the wrong approach. You've got to look at this as a regime shift. So it's a kind of a full state thinking rather than a linearized thinking. So that's just a sort of a cautionary tale that it's always good to look at the full state. I think that's a good lesson before you start, taking out a mean and looking at anomalies, because it will affect how you interpret, autocorrelations and stuff like that, and how you would do a noise model. Okay, I was going to say something about variations. I took longer than I thought I would there. So we've seen that this equation. We have a forcing. If you integrate over the vertical, in the equation I showed before, it was from the primitive equations, and you have a Coriolis torque term in the tendency, but in the QG version of this, you don't have a Coriolis torque term under the QG scaling, so you just have momentum fluxes, and then of course you can have a friction. So this is Lorenz and Hartmann came up with this very simple model for that. You just Z is the zonal wind. It's going to be the southern annular mode. M is the momentum flux convergence, and they assume that the F acts as a damping on the SAM. And so this actually, I wrote this before I heard Hank's lectures. This goes back to the Hasselmann model that we've heard a lot about, of course. And the idea here is that the eddy forcing, which is the eddy momentum flux, is the white noise coming from weather systems, but that's driving lower frequency variability in the southern annular mode. That's the red noise. So if you plot, of course, if you just take a spectral transform of this, you can write that equation this way. And if you then plot the real and imaginary part of this quantity here, you can see that there's a constant which gives you the damping time scale, and there's this nice straight relation against frequency. So it seems to fit the data very well, at least in the southern hemisphere. Oh, that's the wind actually. So it's kind of a unfortunate. I guess I didn't write it. Yeah, sorry. So Z is the vertically averaged wind. Yeah. Usually it's something else, of course. Right, so it seems to work, and if you look at the phase difference, so this is versus frequencies, at the higher frequencies you see that they're 90 degrees out of phase because you're in the transient part where this is the balance, but as you go to the long term, M and Z go into phase, and that's shown here. So it seems to work quite well with the observations. But one of the things that Nick pointed out in this earlier paper was that actually if you look at the power spectra of the southern hemisphere, there's this pretty strong 2-year peak. And we haven't, well, you know, Nick didn't want to do a red noise test because he doesn't like, he's worried about filtering, but I don't think you have to do it. I mean, it's, so this is the power spectrum of, oh, I didn't write it. This is the SAM, or the wind, and this is the eddy momentum flux. So sure, there's this peak in the synoptic scale time scales, as you expect. This is your weather noise, but there's this big spike here. Now, Lorenz and Hartmann argue that this was coming from a feedback, but Nick has convinced me, and I guess the reviewers, that this is an artifact, and at least for this data set, and that you can get this bump. So this bump has been interpreted as a, so of course the eddies drive the wind. That just follows directly from you know this equation. But then the question is there a feedback? And they interpreted this bump here at the positive lag as a feedback, and he's argued it's an artifact, the fact you got low frequency. Now, of course, if you're in the southern hemisphere and you've taken out the annual cycle, 2 years is the next period, and you've got the QBO, and also the fact in the southern hemisphere, because of this vortex breakdown, the variability is all in one time of year. So it's plausible that it's stratospheric. Okay, I want to finally finish with a cautionary note for modeling. Sorry if this is confusing. So this is the challenge for the hierarchical approach. So before Ina joined my group, she did a PhD on extrasolar planets and exoplanet atmospheres. And one of the things she did was an intercomparison. You've heard of lots of MIPS. Well, I guess this was an exoplanet MIP. And they did this idealized setup for a hot planet, you know, very, very high heating and tidally locked. So you have warming over the western hemisphere and cooling over the eastern hemisphere, and a fixed day-night. This is just the angular momentum, and a bunch of different models. The spectral models conserve angular momentum exactly as they will, of course. The MIT GCM in lat long conserves if you go to high enough resolution, but the cube sphere is a disaster, and they get all sorts of spurious. It makes sense. They've broken a rotational symmetry, right? If you have, and I don't ask me what the cube sphere is. Maybe someone here knows, but it's a way to, people are interested in regridding, and this is a way to come up to avoid the pole problem, because the problem with the lat long grid is you have a pole problem, which creates the numerical problems. So this is an approach called the cube sphere. But obviously a cube, well, it's got a discrete rotational symmetry, but it's not got a continuous rotational symmetry. And and so this is it's just, this is a problem. And the thing that really worries me is that not that people use the MIT GCM with cube sphere necessarily all the time, but they are using cube spheres, and because of the exascale computing challenge, people are moving. All the big centers are moving to grids that can where the what's the term that they scale properly with the resolution, which is forcing pretty much everybody into things like icosahedral grids. These break rotational symmetry. And there's a big program in Britain involving all the mathematicians called Gung Ho, where they conserve vorticity, so they have all the mimetic conservation. And I said, well, you've got energy and vorticity, but you lose momentum. They said, well, we can't conserve everything. But it worries me because every explanation I've been talking about involves angular momentum. And people didn't seem to have thought about that. The people doing the dynamical cores don't tend to talk to the people doing the parameterizations and things. And so, yeah, I'm kind of worried if this is an important mathematical challenge, perhaps, is to find grids that actually will preserve rotational symmetry, but will have the right kind of exascale scaling. Another thing, so that was so models can differ because of dynamical cores. The other thing has been so you could say, well, if we're going to have a hierarchy, maybe the models are disagreeing. I don't know, because of topographic blocking or something. So let's have a very simple thing. So there was something called the Aqua Planet experiment that was actually, I guess it was Huskin's idea originally, and Mike Blackburn really led it. And there's a special issue of the JMSJ in 2013. In this case, you run, so Aqua Planet I've already talked about. So the idea is let's run GCMs under identical forcings with imposed SSTs. This is atmosphere only, and see if we get the same answer. This is just an example. That wasn't part of that comparison. This is by Stevens and Boney, published in Science. They just, I don't know if Caroline showed this possibly. If you just warm, did she? No, okay. If you just warm an aqua, oh, well, I'll show it again anyway. So you take these different models. These are all state-of-the-art CMIT models, and you apply a uniform 4-degree warming in an Aqua Planet with prescribed SSTs. These are the cloud rate effects, and maybe more importantly, for climate, this is the precipitation change, and they're all over the map. So you try to run the models under identical conditions, and they give completely different answers. And actually, the biggest difference is between Bjorn's model and Sandrine's model, the IPSL model. I guess these guys fill in the difference. This is really worrisome. I mean, how do we know if you can't? You might say, well, we can't do good theory of the atmosphere, but maybe we could do good theory of models. But yes.
Would you mind going back just one slide? Sorry about that. Having trouble connecting the symmetry of the grid to what you conserve. So I get that you have a symmetry of a Hamiltonian, gives you an implied conservation law. Mm-hmm. But even on a sphere, when you have topography, you don't have perfect spherical symmetry.
Well, and you don't conserve momentum because of surface torques, but you conserve momentum in the free atmosphere.
Okay.
So sure, you're going to have, I mean, it's not that you conserve, I mean, I've talked about momentum budget. Surface drag is important, mountain torque is important. But just like with when we talk about the wave activity equation, there's a conservative part and there's a non-conservative part, and you better handle the conservative part properly, or you're going to get spurious sources or sinks. That's the kind of argument. I mean, no one has a Hamiltonian formulation of a discrete truncation of the equation, so I can't say that the conservation of angular momentum in a numerical model comes from rotational symmetry necessarily. But of course, the way that you set it up, I mean, you can just imagine that if your grid points are along a line of constant latitude, there is a rotational symmetry. Okay, it's not continuous, but as you go to higher, resolution, and actually just the way that the spectral scheme is done, you conserve it. But I think that if this is a hypothesis, but it seems to me if you have a grid that breaks rotational symmetry, you're going to have a very hard time. You're building in a sort of a non-conservation even in the adiabatic part of the system, which I think has to have consequences. So I think that's an interesting question. Okay, so I want to finally just at the 10:30 point. So I just want to finally go over the whole week quickly. I should have done this on the first day. Hank inspired me that this is, if I ever do this again, I would show this every day. So we started the first day. We want to look at the phenomenology. Very important to know what the key pieces are. So on the Earth, we've got the Hadley circulation, of course, very, very important feature, and then we've got mid-latitude baroclinicity. And so we know that those are the main ingredients, and the baroclinicity is going to drive eddies through baroclinic instability. And then we see that in the heat fluxes, the poleward heat fluxes, and then as we saw from the observations, as the zonal jets have a positive eddy momentum forcing. They get accelerated by the jet, what used to be called the maintenance of the westerlies problem. Then we had two different streams, if you like. Then on the lectures 2 and 3, I talked first about the balanced and unbalanced dynamics and the vortical dynamics and inertial gravity waves and the slow manifold idea. And then two-dimensional and shallow water turbulence, where we have a combination of, in the shallow water case, we have a combination of unbalanced and balanced dynamics. And so the balanced part, we have this upscale energy cascade and a downscale entropy cascade. And talked about the gauge Naismith spectrum and the controversy. You'll hear about, I'm sure you'll be hearing about one side of the controversy next week. And then we switched over to Hamiltonian geophysical fluid dynamics and the concept of pseudo, so I'm going to call it pseudo momentum. I don't know what to call them, okay? They're not Rossby waves, because they're not waves, so let's just call them beta plane eddies, or if you like, find an amplitude Rossby waves. And actually, you'll hear a lot about this from Bill. Bill is not fond of this term for some reason, but it's the same thing. Vorticity, variance. You could call it potential entropy, but it's what I'm calling pseudo momentum. It all goes back to this G.I. Taylor formula. So let's avoid controversy whether they're waves or not, and just call them beta plane eddies. And then talked about the wave mean flow interaction theory and this non-acceleration theorem. And I should have made clear, and I hope it was, I guess it was implicit. People have talked about streaming. Some of the students were talking about streaming and grad waves. It's the same thing. This non-acceleration theorem tells you that you need transients or a dissipation to generate a mean flow. There will be maybe some exceptions that Oliver might talk about, but basically this is the thing. So it doesn't matter if it's a Rossby wave or a gravity wave or an acoustic wave. You can generate mean flows by a dissipation of waves, and that's the non-acceleration theorem. So it really is a unifying principle, and you can see from the Hamiltonian perspective that it's connecting the momentum or the symmetry, the invariant connected with a translational symmetry with the pseudo momentum, and you can derive this. If you look at this at my review papers, I write it all down for the primitive equations and the Boussinesq equations and everything, and then argue that in the end, of course, in the atmosphere case, we have a Ross wave source. Well, if you have a source, it'll drive westerlies, and a sink will drive easterlies. And then finally today, talked about eddy-driven jets, talked about eddy-damped jets, and finally, that in the Earth's atmosphere, things are even more complex because you have to fit this in with everything else. Thanks very much.
So here, so you talked about the transient eddy gain energy from the mean flow and NSC give energy, extract energy from the mean flow, right? Or vice versa.
Yeah, or vice versa.
So I'm curious about like how do Ferrel cells respond in the mid latitudes, because we know that Ferrel cells are driven by eddies.
Don't think about the Ferrel cell. It's not worth thinking about. It doesn't exist. How's that for an answer? I mean, tell me why the Ferrel cell is important. I mean, maybe you can have an argument, but one of the things I learned at MIT, where I was taught all about the Ferrel cell, but I eventually learned don't think about the Ferrel cell. It just confuses things, I think. Maybe we can have another discussion about that. So okay. I just have refused to think about the Ferrel cell. You don't need to, and I think it's simpler without, actually. But I'd be happy to talk to you about it afterwards. I'm from the TEM camp, transformed layer and mean.
So I think it's time to thanks again Ted for this very nice lecture.
Well, thanks very much. It's been fun. I'm exhausted. I don't know how you guys are going to handle 4 weeks of this, but I'll be leaving at 2. So if you want to, I'll be around over lunch and a little bit after lunch. So if you want to check up, talk to me, I'll be out here through to 2. Thanks.
Thank you.